Today, I will do you a solid by talking about solid design principles. Solid principles are these five object-oriented design principles. Their purpose is to improve maintainability, improve testability, improve flexibility, as well as scalability. It facilitates loose coupling and makes databases more robust. Why do we care about this? Because there are situations where small changes can break unrelated code. So a small change could crash the entire program. It may be difficult to test if certain principles are not followed. These so-called God classes, these classes that are all-encompassing, tend to grow over time and become bloated. However, solid principles enable easier refactoring, debugging, and onboarding. S is the first principle. That stands for single responsibility principle. It means that each class only has one job. A class should only have one reason to change. It improves readability and testability and keeps our business logic separate from infrastructure. Okay, let's move on. So let's look at our example. We have a single class which saves user data. We have a single class which sends email. We have a single service class for our user. The next principle is O for open-closed principle. Open to extension, but closed to modification. That means that you should be able to add behavior without modifying the existing code base. And we use interfaces, child classes, and of course composition to achieve all this. This is an example using an interface. As you can see here, there is an interface called payment method, and both credit card payment and PayPal payment extend this payment method. And the way that we're extending and not modifying is we're not changing existing code, but we're creating classes that implement this, this method. So they implement this abstract method called pay and add their own implementations. So this is what it means to be open to extension but closed to modification. Instead of making changes, we extend off existing code. Next, we have the L for Liskov Substitution principle. This means that child classes are substitutable for parent classes. And by doing this, you don't get any unexpected behavior. And this is because the child classes inherit the parent's behaviors and they have their own behaviors as well. So let's talk a little bit about Barbara Liskov. She's famous because she's one of the reasons that we have this object-oriented design, including this substitution principle. She's an American computer scientist and MIT professor who won the 2008 Turing Award. That's basically the Nobel Prize for software engineers. She pioneered abstraction and introduced this principle that we're talking about now. And this is one of the foundational rules of object-oriented design that ensures that subclasses can replace their parent classes without breaking the code. Here's an example. We have a shape interface, and we have rect and square, which implement shape. And this shape is known as the reference type. So any class that implements this interface can be substituted. So any class that implements this interface is substitutable. Next is the interface segregation principle. So essentially this means that classes should not depend on method or code that they don't need. And essentially, we prefer small specialized interfaces as opposed to fat interfaces with many methods that we will not need. This is essentially the single responsibility principle for interfaces. Here's an example of the interface segregation principle. We have two interfaces, two specialized interfaces. We have a specialized interface for working and a specialized interface for eating. And we have two classes that implement these interfaces. Humans need to work and eat. Robots just need to work. They don't eat. Last but not least is D for dependency inversion principle. It means that we rely on abstractions rather than concrete implementations. High and low level modules depend on interfaces. So this dependency inversion principle is largely achieved by using interfaces. And it allows us to mock, test, and perform dependency injection. So here's an example of the dependency inversion principle. So we have an interface called payment gateway, which has an abstract method called charge. And essentially what we're doing is we're relying on this abstraction rather than concrete implementations. So the concrete implementations come when you have a class that extends this interface. And when you extend an interface, you're bound by contract to implement their methods. So they're going to implement the charge method, but they can do it in their own way. They can add their own implementation. That's where the abstraction comes from. We don't care about the details of how this method works. We just care that it works. Yes, so we depend on abstractions. Any class implementing the interface may provide its own concrete implementations. Here's a way to remember these. So S, you got one job to do. Each class only has one job. O, open close. You don't modify, you extend. L, Liskov substitution principle. The child behaves like the parent, therefore you can substitute it. I, interface segregation principle. Small, specialized interface, not the fat ones. D, dependency inversion principle. We depend on abstractions rather than concrete implementation. So we depend on interfaces. Right, everybody, we are back in Eclipse. Let's take a look at this God order service class, which just looks god-awful because it's pretty much violating every single part of the solid principle. Every one of the solid principles is being violated. Okay. So what we're going to do is break these into classes. So the order of refactoring is single responsibility principle, then open closed, dependency inversion principle, interface segregation principle, and Liskov substitution principle. So let's handle it in that order. So first, single responsibility principle. So let's break these into classes. Get rid of this class. Next, we address the dependency inversion principle. So we're going to create some interfaces, more interfaces. Right, so now we have order manager dependent on abstractions. All right, let's review what we've done. Okay, so the first thing we did was we refactored the classes according to their single responsibility principle. So we gave each of those tasks in that God level class their own class. So that's what we did. Okay, so these are the individual classes. Okay, and then what we did is we used the open close principle and we used it to remove all those if else chains and just abstracted it into an interface with one method, which is pay. And then we have two concrete implementations. We also have a payment processor. We then use the dependency inversion principle to create interfaces that would be implemented by those classes. So now this should be fully testable. So now we have things set up. Let's do a little cleanup. So now all these classes are going to implement their respective repositories. So let's move all this stuff down a little further where we can see. So this will implement tax service because it's going, this is the concrete implementation of this. All right, looks like we're done here for now. All right, after a little more cleanup, we have our four interfaces. We have our concrete implementations. Payment processor, and we have the refactored God order manager class, which is now refactored into an order manager. So as you can see, we have separate, smaller, dedicated interfaces. We have concrete implementations, which rely on abstractions rather than concrete implementations. And this also shows you don't really need to override, but I'll put it. There is so much refactoring. Okay. Payment processor. And this payment processor, what it allows us to do is you can take in any payment method. So now if you want to pay by credit card, you can pay by credit card, PayPal, debit card, any method that extends payment, anything that is a payment method. And then of course we have our order manager class. These two we'll discuss in another. Actually, let's do it now. So this is the interface segregation principle. And as you can see, we have this bloated fat interface called worker with three unrelated methods. And then we have a robot implemented worker. Robot only needs to work, does not need to eat nor sleep. So let's refactor this. Okay, we have three new interfaces. Now let's implement these properly. So we'll call this robot worker. Copy and paste. Human worker. Okay. So robots, all they need to do is work. And human workers need to work, but they also need to eat and sleep. So Now we're following the interface segregation principle. Small specialized interfaces properly implemented by subclasses. All right, let's move on to bird. And obviously the penguin's not going to fly, but it can swim. All right, so this is the bird. Let's make this an eagle. They should be swim, not fly. So now we're done with the Liskov segregation principle. Okay, here's our runner class. So it looks like I just copied and pasted this. I'm not typing this out. But we need to create a MySQL order repository. But notice that the reference type is order repository. So all we have to do is extend order repository. So let's see if we can do that real quick. Okay, now let's add the MySQL order repository. Okay, so here it is. I'm not going to type that out. Just import what we need. We'll save it. All right, let's go to our runner class. Let's see, what's this here? Okay, I see. This only takes 2 arguments. Okay, let's run this, see what we got. Okay, so it looks like after the multitude of refactoring that we just did, I haven't used the word multitude in a while, we have something that works. All right, so this is good. So I hope you learned something. I'm tired and I'm out. Peace.